Alright guys, so we have been talking about customized change of variables, and in my previous video I did a couple of nice examples of just double integrals that you can do using this idea. I want to spend a little bit of time on this video just talking about triple integrals. It's of course a little more complicated because you have 3 variables instead of 2. So here's kind of the setup. Your old variables are going to be x, y, and z usually. And the new variables, in the generic context, we would call those u, v, and w. And we do need to write those old variables in terms of the new variables in order to be able to calculate this price that we have to pay for changing coordinates. It's called the Jacobian. The Jacobian is the price we pay, and it is a sort of a little matrix of partial derivatives. Okay, so we have to take on the first row the partial derivatives of x with respect to u, v, and w. The second row is the same with y, and the third row is the same with z. So this is what we actually have to do. And so I kind of, in my last video, I wrote this down. This is just the 3 terms. When you actually evaluate that Jacobian, this is what you're going to end up with. I thought it might be cool just to practice the Jacobian for spherical coordinates here, so we can see if this seems like a reasonable formula. Of course, the variables in this case are not u, v, and w. They are rho, phi, and theta. But the same formula would certainly apply here. So on the first row of this matrix, I'm going to take the partial derivatives of x with respect to rho, phi, and theta. So with respect to rho, I'm going to get sine phi cosine theta. Okay? With respect to phi, I'm going to get, give myself plenty of room for this, by the way. When I do it with respect to phi, I'm going to get rho cosine phi cosine theta. Right? And when I do it with respect to theta, I'm going to get negative rho sine phi sine theta. Okay? So that would be the first row of my Jacobian. The second row, I'm going to do the same thing for the y variable. So I'm going to get sine phi sine theta, and then rho cosine phi, right? So differentiating with respect to phi in the middle column, okay, and sine theta. And then in the right column, I would have rho sine phi cosine theta, okay? So I'm differentiating with respect to rho in the first column, phi in the second column, and theta in the third column. If you need to pause the video to do these partial derivatives a little bit slower, that's totally fine. For the z variable, well, with respect to rho, it's going to be cosine of phi. With respect to phi, it's going to be negative rho sine phi. And with respect to theta, it's actually going to be 0. Okay? So let's just see what happens. This is quite a big expression, and we're going to use the Jacobian formula over here. So I'm going to take the sine of phi times the cosine of theta and multiply it by this times this minus this times this. Well, this times this is 0. And when I subtract this minus, I'm going to get a plus. There's going to be 2 different rows, 2 different sines of phi, and a cosine of theta. Okay, so there's the first term. Alright, now I go to this term. Don't forget we have a minus on this term. So rho cosine phi cosine theta. And then times what? Times this, which is again 0, minus this times this. So that's actually again plus rho sine phi cosine phi sine theta. Okay? So that's that term. And then finally, the last term would be corresponding to this guy right here. There's a minus on it. So minus rho sine phi sine theta. Right? And then we have to take this times this minus this times this. Okay? So this is going to be negative rho sine squared phi sine theta, and then minus rho cosine squared phi sine theta. This is the Jacobian. Okay, that looks awful. That really looks awful. Let me give myself a little room at the top so I can continue here. Yeah, this doesn't look very, very nice, but remember that we do have a trig identity that we could maybe take advantage of. So we've got, notice first of all, that there is a row squared in every single term that you see up there. So I can cancel this row squared, I can cancel that row and that row and that row and that row and that one as well, right? So we can get rid of all of those at least. And then let's start looking at what we are left with here. So I've got, let's just multiply out this first term here. I've got sine cubed of phi cosine squared of theta, right? And then over here I have minus, what am I going to have here? I have a sine phi, I have two cosine phis, so sine phi cosine squared phi, and then I have sine theta and cosine theta. Okay? And then finally, here at the end, notice I have a double negative here at the end. So there's minus, but then two minus signs in here. So I can turn that into a plus, and it looks like I have plus sine cubed phi sine squared theta, that's this term. And then here I have, what do I have? Plus sine phi times 2 cosine squared phi. I need just a little bit more room. And then finally sine squared of theta. Okay? My hope is going to be that this will simplify. Okay? Now, this term and this term, if you add those together and factor out the sine cubed of phi, you'll be left with cosine squared of theta plus sine squared of theta, which is just 1. Right? So we actually can just write this as sine cubed of phi for the first and third terms. Okay? Now, if we look at the second and fourth terms, right, this term and this term, let's see, what do we have in common on those terms? Almost everything, right? So, let me write this as minus. There's a sine of phi in both terms. There's a cosine squared of phi in both terms. There's a sine of theta in both terms. And the only thing that's different is here I have a cosine of theta right here. Okay? And then I have an extra sine of theta over here. Right? And that one, because this is a plus, I would have to make this into a minus right here. So hopefully I'm doing this right. Let's see if this makes sense or not. I feel like the theta stuff should have disappeared somewhere. So let's just look at this really quickly and make sure I didn't mess this up somehow. Just going to double check my work really quickly. Oh, I wonder if I have a little problem right here on this j component, right? So when I took minus of this term, right? And then I took this times this, which is 0, minus this times this. And you see, it should have been, let me just see. What is that? Minus, so this should have been minus right here. This times this, right? Minus rho times sine phi, cosine phi, and this should have been a cosine of theta right here. That's what I think maybe is the problem that I have right now. So if I go back and adjust that, let's see, this term is okay, right? Then for this term, I have, it really should end up being a plus, right? Because there was I forgot this minus sign right here. So this is really a plus, a sine of phi, cosine squared of phi, and then this should have been cosine squared of theta right there. Yeah, So that's what I missed. That's what I was missing. Okay, so if I go back, sorry, I hope that this is clear enough what's going on. I just made a little mistake on this first step of calculating that term right there. If I go back now with the expression like it is, it's going to be a lot better. Okay, the first and third terms still simplify the same way. But now I can actually simplify the second and fourth terms also, because there's a cosine squared and a sine squared added together, and what's factored out of it is sine of phi cosine squared of phi. Just like that. Okay? And if you now factor out a sine of phi from both of these terms, you'll be left with sine squared of phi plus cosine squared of phi, and that is just 1, and there's your answer. Okay, so it is correct. We got the Jacobian to work out. I just made a little goof here when I did this partial derivative here. Anyway, it's something you can check on your own very easily. The Jacobian for spherical coordinates is rho squared sine phi. Okay, great. So it's a little bit harder when we have a triple integral than it is with a double integral, but in theory it still isn't that bad to work these out. Let me maybe just try a quick example with you really quickly, all right? See if we can make sense of this. So let's do one last example. Okay? So let's do this. Let's find the volume. Find the volume of the region bounded by the square root of x plus the square root of y plus the square root of z equals 1, and the xy, xz, and yz planes. Okay? So this is actually not a particularly nice surface that we would know, but we can turn it into a nice surface pretty easily. What I can do, of course, what I'm really trying to do here is calculate the volume. So this would be the triple integral of 1 dv over this region. But this region is not well suited for us to do the triple integral over, just because this particular surface is not one of our familiar surfaces. But if I do the following, if I let u equal the square root of x, v equal the square root of y, and w equal the square root of z, I might be able to get this to look a little bit nicer. Okay? And so what will actually happen if I do that, of course we also can write the old variables in terms of the new ones. So x would be u squared. This is pretty easy in this case to solve for the old variables in terms of the new ones. If we do that, right, then this will become a much simpler problem, because what you will have now, what you will have here with this equation is simply the equation u plus v plus w equals 1. And that is just, if I think about the u, v, w coordinate system, this is just a plane that goes through, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so this is going to be a pretty nice domain to integrate. Let's see, what else are we going to have to figure out in order to do the volume? Well, we're going to need our Jacobian. We're going to need our Jacobian. I've got the formula right here, so maybe I can just go ahead and run with it. The Jacobian is going to give me, I have to take the partial derivatives of x with respect to u, and then with respect to v and w, right? So there's nothing with respect to v or w. Y is only going to give me a partial with respect to v, and z is only going to give me a partial with respect to w. So if you just do that little calculation of that determinant, this is all you're going to get, 8 UVW. So what you're going to have for the volume is the triple integral of 8UVW dV, all right? And the limits of integration are going to just correspond to this picture right here. So, for example, in the UV plane, in just the UV plane, we have this equation, V equals 1 minus U. It's very easy. I can just integrate U from 0 to 1, and then V from 0 to 1 minus U. That's on the outside, right? And then on the inside, I would do the double U integration, which would start at the base, which is in the UV plane. That's where W is 0. And then we would integrate up to the surface itself, which if I solve it for W is 1 minus U minus V. This would be the setup of the integral in the UVW domain. Okay, so the limits are pretty simple. We would be able to do this integration. I'm going to skip that for now. I just wanted to focus on setting it up. We've got our Jacobian in here, and we've got our limits for UV and W set up. So we're set to go, and we can actually evaluate that integral at this point. Hopefully this makes sense. If there are questions, feel free to shoot me a note. Let me know where you're having any problems with this. Practice some examples on your own, and try some homework problems, and then let me know how we're doing with this. This is 14.8. We're just talking about customized changes of variables. And the hard parts of this are sometimes figuring out what are the equations to use, if they're not given to you already. Sometimes the Jacobian can be messy. Okay, that's a possibility as well. But the whole idea is that the integral that you end up with should not be that hard to evaluate. Your whole purpose here is to make this integral easier to do than what you had started with. So I'm hoping that this makes good sense, kind of the philosophy behind it. But let me know if it's not clear, and I'll take questions when I see you again, or when I get a note from you about anything that you're wanting to ask me. Thanks a lot for watching, guys. I hope things are going well, and I'll see you all again soon. Thanks.